So our job for today is twofold. The first part is going to be to take our understanding of partial derivatives that we've been building for the last two class periods and push the boundaries on it even a little bit more. So in our meeting yesterday, we saw how partial derivatives can help us to, first of all, find equations for tangent planes, linearizations to functions of several variables, and then also help us to use the chain rule, the multivariable chain rule,
Excuse me,
for a
doctor.
composition of two
I have a vision for
multivariable
you.
functions.
Excuse me.
So we saw all of that in our last class. And so part of what that was about was trying to use multiple partial derivatives kind of simultaneously at the same time instead of looking at one of them by themselves. And today is a continuation of that process. So directional derivatives, which is going to be our first topic, is going to be an answer to the question, if we're interested in the rate of change of a multivariable function, not just in the x direction or not just in the y direction, but in some direction that might be in between, at some other angle, how can I get at that question? And so directional derivative is an answer to that question. By way of an illustration, what it looks like, move my head out of the way here.
Matthew, excuse me about the homework.
If I'm asking about a directional derivative, we at every point we have a partial derivative in the x direction, which tells us a slope of a tangent line in the xz plane. We also have a y direction partial derivative that tells me the slope of a tangent line that's in the yz direction. But a directional derivative is going to give us the ability to pick any direction that we like to from whatever point that we're at and find the slope of a tangent line that faces in that direction. So we can go northwest, for example, if we want to. And again, looking at this from above, this is what this looks like. And so I can have the slope of a tangent line to my graph that faces in the northwesterly direction. And in this particular example, that tangent line happens to have a zero slope. So this is a horizontal tangent line, when we would not necessarily have expected that, given that the x partial derivative gives me a tangent line that's not horizontal, and the y partial derivative gives me a tangent line that's not horizontal. But it should be the case, probably, that every tangent plane that we can sketch to a graph is going to have some line in it which is horizontal. And so there should be some direction, always, that we can walk in that gives us a slope of zero. And so those slopes are what we're going to call the directional derivatives. So our job is first going to be to figure out, how can I compute one of these directional derivatives? How do I find the slope of a tangent line that doesn't just face in the x direction or the y direction, but which goes in some direction that is not one of the coordinate directions? So that's going to be step one for us. And then step two is going to be to abstract that out and sort of figure out, all right, how can I come up with a quantity, a derivative, if you like, for a multivariable function that carries information about all the directional derivatives inside of it. Right? Can I have one entity that carries all the directional derivatives, that all I have to do is sort of ask that entity, hey, I want this direction, can you tell me the directional derivative? And it'll do that for me. It's almost like the Rosetta Stone of derivatives for a multivariable function. And that Rosetta Stone is called the gradient of a multivariable function. Probably, for me at least, the single most important type of derivative that we will encounter, because it encompasses every other type of derivative that we would ever be interested in. So it's one of these things that we often do in math, where the last thing that we learn about makes all the previous things that we learned about seem much more trivial after we do, much easier. But that's sort of by design, right? Because we wanted to linger on, what do partial derivatives actually tell us? And then how do I find equations for a tangent plane? And then, how do I use the chain rule? And then, okay, what's a directional derivative? And then at the end of that process, we get this object, the gradient, that is going to have the power to answer all of those questions for us. And so for me, the derivative of a function of several variables has no better embodiment in a single mathematical entity than it does in the gradient. And as we get toward the final act of our course, when we do vector field analysis, gradients are going to be a very important source for us for where we can construct vector fields from scalar valued functions. And some of the reasons for that, I think we'll be able to at least get an initial idea of today as we meet the gradient for the first time. So that's the agenda for what we're hoping to accomplish today.